All right, this is Mr. McCord's chemistry class, Unit 8. We're looking at doing calculations with gas laws. So up to this point, we've seen a couple relationships between pressure and volume and temperature of a gas. These properties relate to each other and change with each other. So as the pressure of a gas changes, maybe its volume is changing or its temperature is changing. As we change the temperature of a gas, perhaps that changes the volume. So we have these relationships. We have scientific laws for these relationships that say, as this changes, the other one changes. And the three fundamental ones we've talked about so far are Boyle's law, Charles' law, and Gay-Lussac's law. Boyle's law deals with pressure and volume, pressure being how much a gas pushes on the inside of its container as those particles bounce around. Volume being the space that the gas takes up in the container, not physically about how much space the particles take up themselves. Charles' law is about volume and temperature. Again, temperature being about how fast those particles are moving and what mass they have. All right, that kinetic energy of those particles is what the temperature is. And we have Gay-Lussac's law, which puts together pressure and temperature. Boyle's law is an indirect relationship. It goes opposite directions. It's inverse. Right? So as pressure is increased, it's because the volume is decreasing. We are shrinking the size of the container so the pressure builds. And then vice versa. If we expand the container and give the gas more room, the pressure drops. Volume and temperature and pressure and temperature, for Charles' law and Gay-Lussac's law respectively, are direct relationships. They go the same direction. So as you increase the temperature, the gas is either expanding the volume of the container or it's increasing the pressure as those gas particles are hitting harder, as they're moving faster. Now, not only can we predict how one thing will change another, what direction it goes, whether something increases the pressure or decreases the volume, we can figure out what the new pressure or volume or temperature is with a calculation. We can actually figure out, all right, what is the new pressure going to be in here if I'm measuring in atmospheres or kPa, that's kilopascals. Physicists like kilopascals because it's great to convert with. Okay, or mmHg. You might see these on blood pressure, those sleeves, and then they, put the stethoscope on there and check you. Okay. So mmHg is millimeters of mercury. It's an old way of measuring air pressure that just kind of the unit stuck around. Okay, what is going to be my new pressure? Not just that it's going up, but is it going to be 2 atmospheres, or is it going to be 250 kPa? What's it going to turn out to be? What's going to be the new temperature of the gas? Okay, so we can do these calculations with these 3 gas laws to mathematically determine what that new property is going to be. And we can also use it to figure out what the original conditions were if we're measuring the new conditions. All right, let's do an example of how we can actually calculate one of these properties. So the example that I have here is I have this little dart shooter, right? That's real simple. It's just filled with air, right? And as I squeeze this, I am changing the volume that the air is in, right? There's also room for air inside the dart, right? With the apparatus together, I've got about a volume of 30 milliliters of air inside this dart shooter, all right? Now, to get the dart to fire, I am going to decrease the volume. I'm going to squeeze the handle, all right? That should, if the temperature is not changing, increase the pressure because volume and pressure go opposite directions. We call that Boyle's law. So I'm going to use Boyle's law to figure out what my new pressure is inside the dart shooter that gets this thing to fire. Not super impressive, but gets the job done. So, my original volume is about 30 milliliters, all right, of air or gas inside that dart shooter. My air pressure inside starts out at about 1 atmosphere. Pretty standard. When I squeeze the dart shooter, I decrease that volume down to about 10 milliliters. And I want to know what that new pressure is that causes the dart to fire. Okay? So, the mathematical version of Boyle's law looks something like this. P1V1 equals P2V2. So my original pressure times my original volume is going to be equal to my new pressure times the new volume. Okay? Whenever you see two variables next to each other like this, that's multiplying. So I'm going to sneak them in this time just so you don't forget. But most of the time you don't see the multiplication signs actually written out. Okay, so this says that as the pressure changes, the volume has to change with it. And from what we know with Boyle's law, as my volume goes down, my pressure's got to go up. All right? Which is why I can relate the original conditions with the new conditions. Okay? So all I have to do is plug in what I know. Well, I know my original volume is 30 milliliters. I know my original pressure inside the dart shooter is 1 atmosphere. So let me plug those in. All right, so my original pressure and volume, 1 atmosphere times 30 milliliters. Then that's going to be equal to my new pressure, which I don't know yet, times the new volume that I have. Oops. Okay, I decreased the volume to 10 milliliters, so I want to know what the new pressure is that accompanies the gas at that point. Okay. Well, at this point, it's just an algebra problem. I'm missing one thing. I want to solve for this variable here, this new pressure. Okay? You can call it P2, you can call it an X, you can write a question mark, you can put a triangle, it doesn't really matter, as long as you know that you're solving for this missing variable, this missing property here. Okay? So we just got to do some math to kind of work this out. Well, if I want to get P2 alone, I should probably divide off that 10 milliliters there. Color. So I'm going to divide both sides by that 10 milliliters. Okay. On the right side, that's just going to go away. Okay. On the left side, if I divide by 10 milliliters, I can work that math out, and I'm also going to cancel my milliliters units. Okay, so the units are going away. I'm going to cancel those out. So I should get an answer that only has a unit of atmospheres, which is good. I'm looking for a new pressure. So I want my pressure to come out in the same pressure unit that I started with. I don't want milliliters anywhere near this answer. If I'm doing something with temperature, same thing. I want to get rid of the units I don't need, and I want to wind up with the units that I do need. Okay? So all that's left from here is to actually work out this math. So P2's alone. Then I'm going to take 1 times 30 divided by 10 to figure out what my new pressure in atmospheres is. Okay, well, 1 times 30 is just 30. 30 divided by 10 is 3. So I come out with about a pressure of 3 atmospheres, right? That's my new pressure inside the dart shooter. And that's my answer. Okay? So, we're going to look at another example where we take a different gas law and apply it to a problem like this to figure out what we're going to wind up with. Okay, this next example is kind of a fan favorite demonstration in my classes. We call this thing a hand boiler. Now, we don't actually boil the liquid inside here. It's kind of a sciencey trick. What we're doing is putting heat into this, the warmth from my hand, right? And that's not boiling this liquid, right? Instead, it is increasing the pressure of the air above that liquid. That air is going to push down harder and harder and harder on this liquid, and it's going to have nowhere else to go but up through this tube, all right? We can do so much that the air pushes itself up through the tube along with the liquid and gives us these bubbles, which makes it look like the liquid is boiling. But in reality, it's just the warmth of my hand pushing the air through with it. Okay? So, that's going to be the basis of this problem. So before I put my hands on the hand boiler, right, the temperature inside should be about room temperature. Right? With gas laws, we like to do everything in Kelvin, so that way there are no negative numbers that can mess up our stuff. We don't want a negative pressure or a negative volume because that's not going to make sense to what we think about. I can't really have less than no space. So room temperature is about 20 degrees Celsius. We bump that up to Kelvin by adding 273.15 to that. My temperature inside my hand boiler should be about 293.15 Kelvin. My pressure of the air inside, we're just going to say is about 1 atmosphere. So if this is enough to raise the pressure up to 1.07 atmospheres, I want to figure out what the temperature is of that gas inside. After all, I can't really get a thermometer in there. Now also, since the container is rigid, the volume shouldn't be changing. So in this case, we only have pressure and temperature changing. So I can pick a gas law that best fits this situation. If pressure and temperature are changing, but volume is constant, I'm not changing the size of the gas's container, then this is fit for Gay-Lussac's law. Okay? Mathematically, since pressure and temperature go the same way, we show that by putting P over T. So if one of them is going up, the other has to go up in order to equal the same kind of setup on the right side. Okay, so this is Gay-Lussac's law. The stuff I have to plug in is my original temperature, my original pressure, and the new pressure inside here. I want to solve for this new temperature, which is going to be a little tricky because it's on the bottom here. So let's plug everything in and see where that takes us. So I need the parentheses here. Okay. New pressure over here. Again, you can write T2, you could write an X, whatever, as long as you know you're solving for this missing variable. Okay. Well, I don't want to end up with this T2 being on bottom. I want to get it out of the denominator as fast as possible because I don't want to know what 1 over T2 equals. I want to know what T2 equals. And it's not the same thing. It's flipped upside down. So we're going to do some algebra first to get that fixed. So if I multiply both sides by T2, right, I should be able to cancel off the T2 from the right side. And now it'll be up on top on the left side. So I'm going to rewrite this, where my T2 times my 1 atmosphere is going to be on the top of the left side. All right, so I've got my T2 up in the numerator, which is good. That means I can solve for it. I can't solve for a variable down in the denominator, but I've still got to do some work to isolate this, to get this T2 alone. So I've got to undo the 1 atmosphere and the 293.15 Kelvin on the left side. So to get rid of this 293.15, since it's being divided on the left, I want to multiply it on both sides. I'll squeeze that in there. Okay, and then I want to divide off this 1 atmosphere to get it away from the T2. Now, I would usually do this in 2 steps, but I'm kind of running out of room. So if this part confuses you, just know that you can do this step and say, that cancels out. Crunch this math together, and that's cool. And then the next step would be to divide both sides by this 1 atmosphere. I'm going to do it in the same step. So we also cancel that off the left side. And I want to divide off the 1 atmosphere over here also. Okay, well, I've got units that can cancel here. So to figure this out, I should wind up with just the unit of Kelvin on the right side, which is what I want. I want to figure out the new temperature here. So let's summarize this and then solve for it. Okay, so all I have to do now is take my 1.07, I cancel the atmosphere's unit out, so it's just a number, times 293.15, and divide it by 1. Again, the atmosphere's unit down there was canceled out. Okay? Dividing by 1 is not going to do anything, so all I have to do is take 1.07 times this 293.15, and I should get my answer. Let me grab my calculator. And while I'm punching this in, you can try it for yourself. Okay, so this is what I got my answer to be. The new temperature inside that hand boiler is going to be about 313.67 Kelvin. In Schoology, a lot of these are going to be multiple choice. So if your rounding takes you to a different answer, but it's still pretty close, you're just picking the closest one. If we do open response questions and you get, a decimal and you're like, I'm not sure that's it, I will be able to check your math and figure out if you got it right or not. Having a couple decimal points off is not really going to change much. So just go with what your math tells you. These three gas laws, Boyle's law, Charles' law, Gay-Lussac's law, can be used for a lot of different situations in chemistry, since pressure and volume and temperature are usually the three properties we think about most for a gas. But they're not the only ones. There are other gas laws that help us in other situations. For instance, pressure and volume and temperature changing is what those three gas laws look at. But sometimes we want to know just the pressure or just the volume or just the temperature at a certain given time. There's also one property we're kind of avoiding up to this point in the math, just because we've kind of had our hands full with new stuff. But the amount of a gas also plays into this. So this last part here is going to be about that, how the amount of a gas affects the volume of a gas. Okay, so it should be pretty self-explanatory. If you think of a balloon, or in this case, I've just got a rubber glove, if your amount of gas in a container is increasing, if I can hold it off, try again. Then the volume of that gas should also increase. Okay, so and then I could go and continue to change the temperature and the pressure and whatever, but there is a relationship between the amount of gas and the volume. And if I were to let that amount of gas escape and I lose that amount of gas, then my volume should also decrease as well. So this last gas law we're going to talk about in this video, there are others, is called Avogadro's law. Avogadro is the guy that figured out the mole, that 6.02 times 10 to the 23rd particles is what we call 1 mole. All right? It's how we summarize a great deal of particles, and basically what makes us allowed to figure out how the amount of something relates to something else in chemistry. Since we're not going to go and count all the particles, you're going to figure out there's absolutely no way. So, in order to figure out how much gas is in something or how much volume that amount of gas should take up, we use moles, just like we've been doing with a lot of the stuff in stoichiometry before this. It's just a nice convenient way to count an amount of a chemical. So, Avogadro's law, right, works kind of like Charles' law and Gay-Lussac's law, where we have the variables following each other, okay? The amount is directly related to the volume of the gas. If I have more gas particles, they should take up more space if that container is flexible, okay? So my gas law should look really similar to those two other gas laws. Charles' law and Gay-Lussac's law both had something over temperature, right? Volume over temperature or pressure over temperature. So I want something over something to get that same kind of follow each other relationship. So something over something is going to be something over something. I probably want these two to be the same as each other and these two to be the same as each other, where I've got the original conditions over here, something one, and our new stuff over here, something two. Okay? I'm looking at volume and amount. So, Charles' law already has volume in it, and it's up on the top. So maybe we'll just put it there. So V1 over something 1 equals V2 over something 2. Okay, so I need some variable to represent the amount here. Okay, well, we could use A, but that's kind of, I'm not feeling A. Well, we're talking about the amount of moles, so maybe we could do M for moles. but usually we use M for mass, so we probably don't want to do that either. Well, what comes next after M is N in the alphabet, so we'll just kind of settle for that. So to represent the amount of gas, we're using N for moles. And again, that's representing the amount of gas particles that we're dealing with. Also, don't forget that we abbreviate moles to be MOL. Same thing, it just saves us a couple letters. Okay, so this is Avogadro's law. And it works the same way as the other ones. The math is the same, so if our previous examples made sense, this should make sense too. The only difference is we're throwing in a new variable we haven't really talked about yet. But thankfully, it hopefully should make some sense just from your own personal experiences.